Okay, so let's continue with the proof. Now in the case r is less than infinity. Okay, so now we consider m of lambda tf. Okay, which will be the measure of this set x in Rn, so that t of f of x absolute value is less than lambda. Okay, and this measure will be less than equal. This is one of the properties that we mentioned in a few videos before. M of lambda over 2 t f lambda 1 plus m lambda over 2 t f 2 lambda. Okay, this is because we can write f as f1 plus f2, and the property told us that we have to have here lambda over 2 and here also. Okay, and this will be less than equal than c1 lambda over 2 minus 1 Rn absolute value of 1 lambda x dx plus CRR lambda over 2 minus r integral Rn of f2 lambda x r dx. So here we are using that t is weak in 1 1 and r. Okay, so t is weak in 1 1 and in r. So now, okay, this will be equal to 2c1 lambda minus 1 absolute value of f greater than equal than lambda 2 fx absolute value dx plus 2cr r lambda minus r absolute value of f less than lambda over 2 absolute value of fx r dx. Okay, so what we just done a similar thing that we did with the case of r equals infinity. So if you remember, when we did with r equals to infinity, we got this estimate that this was the bound, and we can do a similar thing with what we just did for r less than infinity, and we'll get the following bound. So now we'll have the integral from 0 to infinity, but now lambda p minus 1 minus r, and then we have a integral of lambda over 2 of f of x r dx d lambda. This will give us a bound 2p minus r minus p, and norm p. Okay, so combining these inequalities, okay, and the proposition we used before, we will have that t f p is less than or equal than cp f p. That is what we wanted to know. That is strong in pp. And well, and in this case, cp will be the following constant: pp c1 p minus 1 plus cr r minus p 1 over p. Okay, this will prove the result. Okay, so now let's see what we can use the Marcinkiewicz interpolation theorem. But first, okay, let's denote by L1 log as the space of functions f is from Rn to complex numbers such that the integral k, absolute value of f, dx is less than infinity for any compact k in Rn. Okay, and the volume of the unit ball in Rn will be denoted by omega n, and Brx is going to be the ball of center x and radius r. Okay, notation, and let's define for a given f in L1 log. We defined mfx as the Hardy Littlewood maximal function associated to f, and it will be defined as m of fx equals to this primum or positive 1 over absolute value b r fx ball, okay, and integral in the ball Brx absolute value f y dy, okay, this will be equal to this primum 1 over omega n, which is the volume, again r positive, and now it's going to be the ball radius 1 center 0 f x minus ry absolute value dy, and we can also define it as its primum of r positive f, well, convolution 1 over br not, now the characteristical function br 0 of x. Okay, so some properties of the Hardy Littlewood maximal function. First, m is a sublinear operator. That means that absolute value of m of f plus g of x is less than equal absolute value of m of f of x plus m gx with x in Rn. And another property, if f is in L infinity for n, then norm infinity of m of f is less than equal than f, so it is bounded and the coefficient is 1. This is also telling us that m is of type infinity infinity. Okay.